Today we're going to talk about analog multipliers, how to use them, and some of their interesting applications. Now, a multiplier should not be confused with either a multiplying mixer or an amplifier. Now, granted, both of these things do multiplication, but they multiply an input signal by a fixed constant. So with a diode ring mixer, for example, it typically multiplies the input signal by 1 and -1. And with an operational amplifier, the input signal gets multiplied by some predetermined constant defined by the ratio of its two feedback resistors. An analog multiplier, on the other hand, allows you to multiply two variables, typically labeled x and y. And these variables are usually represented as voltages. So for example, if I put 5 volts into the x input and 2 volts into the y input, the output would be 5 times 2, 10 volts. So this allows us to do some very interesting things that you can't do with other components. So we can do squaring, for example. If my two inputs are the same, then it's going to be, in this case, 5 times 5, which will be 25, which is the same as 5 squared, of course. It also lends itself well to various voltage-controlled applications, such as voltage-controlled amplifiers, AGC loops, and voltage-controlled filters as well. Now, there are a variety of ways that you can achieve multiplication of two voltages, either using discrete circuitry or op-amps. All of those methods tend to be pretty finicky. You've got to have a lot of tweaks, and they also typically do not perform very well over temperature. So usually, if you're going to use one of these in your application, you're going to want to buy a pre-trimmed one. These are laser trimmed at the factory, and they work quite well. And Analog Devices makes a relatively inexpensive component called the AD633, which is a analog multiplier. And it is what's called a 4-quadrant multiplier. In other words, its inputs can be both positive and negative, and its output can be positive and negative as well. Now, the AD633, like most of Analog Devices' analog multipliers, actually has 3 inputs. It has the X and Y inputs, which are multiplied together, but it also has a Z input, which is added to the multiplied values. So this is optional. You don't have to put this in, obviously, but it can be quite convenient if you want to add an offset to the output voltage. And as is typical with most analog multipliers, the multiplication is divided by a scale factor. Typically it's 10, as is the case with the AD633. And for practical purposes, that's just to ensure that the output doesn't exceed the voltage rails of the analog multiplier. So for example, if I put in 5 volts and 5 volts here into both the X and Y inputs, the output would normally be 25 volts because we're multiplying 5 times 5, which means I would have to have typically a plus and minus 25 volt supply, which is a bit much. So if you scale that by 10, then the output would just be 2.5 volts, which is much more manageable. So the AD633 makes operations like squaring an input voltage very simple. You just tie the X and Y inputs together, apply your input voltage, and the output's going to be the input voltage squared, and divided by 10, of course. And this is useful not only for analog computation, but also for frequency doubling. If my input voltage is a sine wave, the output will be a sine wave at twice the frequency. But I can take this a step further, add a second analog multiplier, and cube the input voltage. So I simply take the squared voltage, apply it to one of the inputs in the second analog multiplier, and I take the original input voltage and apply it to the second input. And I get the input voltage cubed divided by 100, because of course this first factor is scaled by 10, and this second multiplier will scale by another 10. So let's hook this up on the bench and see how it works. So all I have here are the 2 analog multipliers with a little op-amp buffer up front, and I'm feeding them with a sawtooth input. And right now I'm taking a look at the output of the first analog multiplier. So that's going to be the input voltage squared. If we move over to the oscilloscope here, you can see there's my sawtooth input. And if I zoom in here on my channel 2, you can see that is the typical curve you get for a squared function. So you can clearly see that the input voltage here in yellow is being properly squared and output from that first analog multiplier. Now I'm going to switch my channel 2 here to the output of the second analog multiplier, and this should be our cubed function. And again, you can see the typical cubic curve on the output. So these chips are doing an excellent job of taking my ramped input voltage, cubing it, and producing a nice cubic plot. And once you start sticking the multiplier inside the feedback loop of an op-amp, you can do even more stuff with it, like division and root extraction. For example, if I want to take the square root of an input voltage, I can put together a circuit like this one. Now, if we ignore the multiplier here, we just have an inverting op-amp with a gain of 1 over 10. So we have R and 10R here. So once we stick this multiplier in the feedback loop, we can see that both the X and Y inputs are tied to the output from the op-amp. So we know that this point is going to be XY over 10, since 10 is the scale factor for the 8633. But X and Y are actually just V out. So really the output here is V out squared over 10. And because op-amps are differential amplifiers, we know that it's going to drive its voltage to ensure that this point is 0 volts, since we have 0 volts tied to the positive input of the op-amp here. So if this multiplier wasn't here, we know that the op-amp would be directly connected to this point, and it would drive this point to be V in divided by 10. So the op-amp is still going to drive its output until this point is V in divided by 10. So we now know that V out squared divided by 10 must equal V in divided by 10. And if you simplify this by multiplying both sides by 10 and then taking the square root of both sides, you get V out equals the square root of V in. Now there are a couple of restrictions to this, obviously. First of all, the input voltage has to be negative since this is an inverted configuration. Obviously I kind of ignored the signs here when I was talking about the gain of the amplifier is 1 over 10. It's actually negative 1 over 10. So if you have a positive input voltage here, this would try and output a negative voltage, but a negative voltage squared is going to be a positive voltage, so that's not going to work. So your input voltage has to be a negative voltage. So to ensure that you never do provide a negative voltage to the multiplier, which would cause a latch-up situation, you usually want to add a diode in the op-amp's output. But aside from those restrictions, this is a really handy way to perform square root extraction. Another very interesting application for analog multipliers is that of a voltage-controlled resistor. So to see how this works, let's first consider this inverting amplifier and pretend like this multiplier is not here. As we decrease this feedback resistor for some given amount of voltage on the output of the op-amp, it will feed back more and more current. So the smaller the resistance, the more current goes through it. That's just Ohm's law. So when we stick the multiplier in the feedback loop of this op-amp, we're multiplying the output voltage of the op-amp by some control voltage. So again, this is hooked up to the X and Y inputs, and the output of the multiplier is going to be XY divided by the scale factor of 10, hence why we again have the 10:1 resistor ratio here. But think about what happens when we artificially increase the voltage imposed across this resistor by increasing the control voltage. So as we increase this control voltage, we're going to increase the amplitude of the signal seen across this resistor. And since the resistor is static, a larger voltage means more current, which is exactly the same situation you would have if you had a fixed voltage and a smaller resistor. So in effect, we are artificially decreasing the resistance of this feedback resistor by amplifying the voltage through this analog multiplier. So this lends itself very well to applications where you need a voltage-controlled amplifier or a voltage-controlled filter. And to demonstrate this, I have that same circuit built up on the breadboard here with just a little trim pot that allows me to set the control voltage supplied to the analog multiplier. So right now I have the control voltage set at 1 volt, and if we look over at the scope, you can see that my input, which is the yellow trace in channel 1, matches very nicely with the output in channel 2, which is the green trace. But as I increase that control voltage, you can see the output starts to decrease. And so we're attenuating more and more that input signal because that feedback resistor is effectively getting smaller and smaller. And this is really just a very small sampling of what you can do with an analog multiplier. They really are very versatile chips. So look for them to be used in some of my upcoming projects. And, as always, please leave any questions, suggestions, or corrections in the comments section below. Thanks for watching.